The Earth's optical system begins at the boundary between the atmosphere and the ocean. As incident solar radiation enters the atmosphere, it interacts with the gas molecules suspended in the air. Lord Rayleigh's atmospheric model formalized this interaction. He demonstrated that the efficiency of this scattering is inversely proportional to the fourth power of the wavelength. Because blue light has a much shorter wavelength than red light, it scatters more intensely, giving the sky its bright blue hue. Rayleigh then extended this logic downward to the ocean surface. He assumed the vibrant blue of the water was a mirror-like reflection of scattered atmospheric skylight. But observational data contradicts this. Even under thick, overcast skies that cast entirely gray light downward, certain deep ocean waters maintain a distinct blue hue. The reflection hypothesis fails because it ignores the massive volume of photons that penetrate the air-water interface and interact with the liquid medium below. Rayleigh's framework relied entirely on elastic scattering. In an elastic collision, a photon bounces off a molecule without losing any energy, meaning its color remains exactly the same. To determine the true source of the ocean's color, physicists had to look past the surface reflection and analyze the internal optical properties of the water itself. In 1921, physicist CV Raman booked a sea voyage where he directly tested Rayleigh's reflection hypothesis. By using a polarizing prism, Raman physically blocked the surface reflection of the sky from his line of sight. He observed that the vivid blue color remained, proving it emanated from within the water volume. The ocean's color is driven by the backscattering of sunlight by the H2O molecules themselves. But Raman observed a critical discrepancy in this backscattered light. While the majority of the scattered photons maintained their original frequency, a small fraction emerged with an altered, lower frequency. This phenomenon is known as inelastic scattering. An incoming photon physically exchanges energy with the molecule during the collision, changing the photon's outgoing color. To see exactly why this happens, we have to derive the mathematical mechanics behind this inelastic shift. This discovery established that the color of a liquid is a macroscopic expression of the subatomic energy exchanges occurring within its molecules. We can isolate the optical mechanics by looking at a single diatomic molecule in a vacuum as it responds to incoming light. In classical electrodynamics, the molecule's response is governed by the dipole equation, where the induced dipole moment, P, equals alpha times the incident electric field, E. That alpha term is the polarizability tensor. It defines exactly how easily the molecule's electron cloud can be distorted by the incoming electromagnetic wave. In standard Rayleigh scattering, this tensor is treated as a static constant. The molecule absorbs and then re-radiates at the exact frequency of the incoming light. But real molecules are never entirely static. Their nuclei constantly vibrate back and forth along the internuclear axis at a specific frequency, denoted as omega v. This constant vibration forces us to rewrite the polarizability tensor as a time-dependent function, combining the static alpha 0 with an oscillating component driven by the frequency of the vibration. The internal mechanical movement of a molecule alters its electrical response to incoming radiation. To see the result of this interaction, we multiply our new time-dependent polarizability tensor by the oscillating electric field of the incoming light. This produces an equation whose Hoare rests on the multiplication of two cosine functions, the frequency of the molecule's vibration and the frequency of the incoming light. Using trigonometric expansion, the product of these two cosines splits into two distinct additive components. Mathematically, the molecule is now forced to radiate at two new frequencies, the original frequency plus the vibration, and the original frequency minus the vibration. The central, unchanged frequency is the elastic Rayleigh scattering. The newly shifted frequencies, displaced equally above and below the original, represent the inelastic Raman scattering. Notice the mathematical symmetry in this classical derivation. It predicts that the higher frequency shift and the lower frequency shift should radiate outward with exact equal intensity. But physical experiments show a massive asymmetry. The lower frequency shift is vastly more intense than the higher frequency shift. Classical electrodynamics fails to account for this discrepancy. To explain the asymmetry, the framework must shift to quantum mechanics. We must treat the incoming light not as a continuous wave, but as discrete packets of energy, photons, possessing an energy defined by Planck's constant times the frequency. Under this framework, the scattering event is a transition between discrete vibrational energy states mediated by a temporary virtual energy state. In what is called the Stokes pathway, a photon excites a ground state molecule up to a virtual state. As it drops back down, the molecule settles into a slightly higher vibrational state than where it started. To conserve energy, it emits a lower energy photon. The anti-Stokes pathway is the opposite. The molecule must already be in an elevated vibrational state before absorbing the incident photon. It then drops to the ground state, emitting a higher energy photon. At normal temperatures, the overwhelming majority of molecules reside in their lowest possible energy state. This population difference solves the asymmetry. Because nearly all molecules start at the ground state, the lower energy Stokes transition is highly probable, while the higher energy anti-Stokes transition is exceedingly rare. This proof of discrete quantum state transitions earned Raman the 1930 Nobel Prize in Physics. By bridging classical wave theory and quantum probability, Raman scattering allows researchers to calculate the specific vibrational architecture of a molecule based on the light it returns. Bringing this quantum behavior out of the vacuum and back to the dense environment of the liquid ocean changes the scale of the effect. Liquid water does not vibrate at just one frequency. The interactions between the densely packed molecules create a complex multitude of closely spaced quantum vibrational states. Because of these overlapping states, Raman scattering in the ocean does not produce a single sharp emission line. It produces a broad, continuous spectrum of shifted light. This set of diagrams graphs the incoming light alongside the resulting Raman emission band. The shaded right triangles represent an inelastic pump. The scattering process removes energy from a narrow, high-frequency excitation spike, depositing it across longer visible wavelengths. The ocean acts as an active optical engine, continuously absorbing, shifting, and redistributing solar energy from the blue end of the spectrum down into the green and red. Today, optical physicists rely on orbital radiometers to measure the ecological health of the global ocean from space. But these satellites consistently detect an excess of photons returning in the green and red spectrums, an influx of light that cannot be accounted for by simple reflection or elastic scattering. To correct for this, scientists must calculate the Raman scattering coefficient. This equation integrates the narrow, high-frequency input band being pumped down into the target wavelength being measured. By mathematically stripping away this quantum baseline generated by the water molecules themselves, researchers can isolate the true absorption signatures of phytoplankton and dissolved organics. Failing to compute this inelastic shift would result in heavily distorted measurements, corrupting our data regarding the Earth's carbon cycle and the health of the marine biosphere. Analyzing the global macro-scale ecosystem relies directly on correctly mapping the subatomic quantum mechanical vibrations discovered by CV Raman over a century.